This video is a continuation of the weak base strong acid video, and we are going from the equivalence point on. So the first thing we have to remember is that we are going to do stoichiometry first and then equilibrium second. And then this is where we're starting at the equivalence point. Okay, so this one's at the equivalence point, which you need to remember that the moles of hydroxide are going to equal the moles of H+. And you are not supposed to use Henderson-Hasselbalch because it will not work. What we're going to be doing is writing a new equation with the conjugate plus water. So let's go ahead and do the work for that. All right, I'm going to clean all of this up first. All right, so now we're going to use 50 milliliters as HCl. And I was just thinking, you don't have to know ahead of time that you're at the equivalence point. I'll show you how you'll know. So 50 milliliters of HCl. Remember that the strong acid reacts with the weak base, which is ammonia. So stoichiometry first. Still have 0.1 molar, so 50 times 1 is 5 millimoles. If you remember from our calculations before, we had 5 millimoles of ammonia. Okay, so you will now know you're at the equivalence point because these two, H plus and OH minus, or acid and base, are equal. So you're at the equivalence point. Now, for a weak acid strong base or a weak base strong acid, the pH at the equivalence point is not going to be 7. So you have to continue calculations. So each of these would go down by 5, which you don't actually have to show if you say that you're at the equivalence point. The conjugate goes up by 5, so you have 5 millimoles of ammonium left. Now, I would recalculate molarity. So 5 divided by 150 gives us 0.033 molar. All right, now take a look at this. Strong acid is no longer there. Weak base is no longer there. So all you have left is ammonium and the chloride ion, which we're not including. Now, because ammonium is an ion, you know that you've also got water that's present. So we have to write a new reaction. Now, we cannot do ammonia plus water. And the reason for that is because we don't have any ammonia. So we can't use that same equation that we've been using over and over again. But we are going to use ammonium because that's still there. So this is like when we did the pH of salt solutions. Ammonium was a conjugate acid, so it's going to give a proton to water. So you're going to get ammonia and H3O plus. If we draw our fence and get rid of water, the only thing we had left was ammonium, and its concentration was 0.033 molar. We had no ammonia and we had no hydronium. Okay, I can't use Henderson-Hasselbalch because I only have the amount of 1. I'm not using POH because I have hydronium over here. So I've got to do some different work. The reactant side will go down by X, product side will go up by X. So I will get 0.033 minus X, X, and X. Now, you got hydronium, so we're going to use a Ka. That will be 1.0 times 10 to the negative 14th, divided by the Kb for ammonia, because they're conjugates of each other, which is 1.8 times 10 to the negative 5th. When we do that, okay, this gives us, whoops, sorry, lost my pen. 5.6 times 10 to the negative 10th. That is equal to x squared divided by 0.033 minus x. Okay, so if I take Ka times 100, it is way smaller than 0.033, so I can approximate. When I do that, I'm going to take 5.6 times 10 to the negative 10th times 0.033, and I will get, I'll go over here for room, x squared equals 1.87 times 10 to the negative 11th. If I do the square root of that, I will get x equals 4.3 times 10 to the negative 6th. Now that's a molarity. That gives me hydronium. I could also calculate the others if I wanted to, but I don't want to. I do want pH. I'm going to do negative log of H plus, which is 4.3 times 10 to the negative 6th. So when I do the negative log of that, I get 5.36. Now, that should make sense because I'm titrating the weak base with a strong acid, so the pH at the equivalence point should be acidic, which it is. Okay, so let's keep going. Now what we're going to do is we are adding even more HCl. So we have overrun our endpoint. So now we're going to do 60 milliliters of HCl. Now we are still adding the strong acid. It's still going to react with the weak base. The amount of the weak base has not changed. That is still the same amount that we originally started with. And we had 100 milliliters of 0.050 molar HCl, if you remember, or not HCl, it was ammonia. So if you remember, this was 5 millimoles. I'm not going to go back and do the work, but that's what we had. I do need to calculate the millimoles of HCl. So 60 milliliters times molarity, which was 0.1, that gives me 6 millimoles. Now I need to get rid of all of this other work over here. And let me go back and draw my fence so we're all looking at the same thing. Okay, so initially I had no ammonium. Okay, when I look at this, I have 6 millimoles and I have 5 millimoles. So at this point, the ammonia is limiting. So this is where the buffer has reached its capacity. It can't consume any more strong acid. And so now what's going to happen is the acid predominates and pH is going to change. So reactant side goes down by 5, product side goes up by 5. I have 1 millimole of HCl left, no ammonia left, and 5 millimoles of ammonium left. Now, no ammonia. So let's get rid of this. Okay. I have 2 acids. I have the strong acid and I have the conjugate acid of the weak base. But a strong acid is still much stronger than this weak conjugate acid. Even though this is stronger than water, it's not as strong as HCl. So I am now in the situation where I just did my stoichiometry first. But I am now in the situation where we're right here. And it says anything beyond the equivalence point will show excess strong remaining. That's where I am. I have excess acid right now. I'm not using Henderson-Hasselbalch. I'm not using an ice chart because I've got strong, and I don't use ice charts with strong. So I am going to take the moles of leftover hydroxide or H+. I'm dividing by the total solution volume to get molarity, and then I'm calculating what I need, pH or POH. So going back to the problem, I need to calculate molarity. So originally I had 100 milliliters of ammonia, so now I've got 160. So I'm doing 1 divided by 160, That gives me 0.00625 molar. I can ignore this because the effect is going to be negligible. I now have the molarity of H+, so I can calculate pH. I can do negative log of 0.00625. And when I do that, I get, okay, let's pay attention to Sig Figs. I don't think I've been paying attention to Sig Figs at all during this video, but I'm not going to go back and redo it and fix it. With the original numbers that I gave, we had 0.10 with our HCl, so we need 2 numbers past the decimal, which I have been doing all along. So the pH at this point is 2.20. Okay, so just for the sake of having a nice graph, what I'm going to do is I want to look at, what if we had 75 milliliters of HCl. So 75 milliliters of HCl. If we remember, we had 5 millimoles of ammonia. And let's get rid of this other work. Okay, that's gone. I'm going to get rid of this. Now, I'm still past my equivalence point, so the strong is going to predominate. Whoops, I did need that 5 millimoles. I didn't need this amount, because when I take 75 times 0.1, I get 7.5 millimoles. So if I look, my buffer, my weak base is limiting. I have no more of it left. It's not there. I have 2.5 millimoles of my strong acid remaining. Ammonia is not there, so I can't use this reaction. Because I'm past the equivalence point, the effect of the conjugate acid is negligible, so I ignore it. So what I do is I calculate the concentration of my strong acid. 2.5 divided by 175 gives us 0.014 molar. So now I want to calculate the pH of that solution. So negative log of 0.014, and I get 1.85. which is the pH when we have added 75 milliliters. Okay, I'm going to do one more video so it's short and you can reference it without having to go back and watch all of this. That's just going to be looking at the graph. This video is probably going to be better than the one that I did with the weak acid, strong base, so you probably want to watch this one.